Hello, everyone. Welcome to today's session of the Porous Media Tea Time Talk. My name is Marcel Morer from the University of Oslo, and I'm joined here by my friend Chiara Recalcati from ELVAG, and the speakers of today, Walid and Moussa. And this is a special session. It's a session to also welcome you to Interpor that will happen in France, in Nantes, in just 1 month. So that's a special session together with the French chapter of Interpor. So before we start, just want to have a quick few announcements here. The first one is that today, actually in just 2 hours from now, we're going to have a webinar from Interpor with Joaquin Jimenez Martinez on how inert phases and active matter shape mixing and reaction in porous media. So this is a free webinar, and you can find the link on the Interpor website. So if you just go on the website and then go, I think here, Academy, and then webinar, you can find the Zoom link there. So it starts at 4 o'clock today, and everyone's welcome to attend. I'm sure it's going to be super nice. And the second announcement is that we got some good news these days from the Brazilian chapter of Interpor, that they are planning to create a Brazilian kind of a Brazilian version of the Tea Time Talk, and that's this here, the Brazil Port Talks, that will be focused on the community of Brazilian researchers working in porous media, both in Brazil and abroad. And the talks will be held in English, and the whole community is welcome to attend. So the first one is on the 28th of April. So we, myself, and the whole team of the Tea Time Talks, were super happy about this. It's nice to see that the ideas of this little seminar series that we host is spreading, and yeah, that's very nice. Okay, so straight to business, so we don't lose much time. Let's welcome our first presenter today, and that is Walid Okaybi. And Walid is a PhD researcher at the Institut des Sciences de la Terre d'Orléans, ISTO, working on the pore-scale physics of clogging in porous media. So Walid is now on the last month of his PhD, and his research explores how flow conditions control particle deposition and structure formation, and how these processes lead to permeability loss in complex systems. His work combines microfluidic experiments, imaging, and flow analysis to connect microscopic mechanisms with macroscopic behavior, with applications in filtration and subsurface systems. So with that, I would like to give the stage to you, Walid. So the floor is yours.
Yeah, hello everyone. Thank you for attending my talk, and I would like to thank as well the Porous Media Tea Time Talks group for giving me the opportunity to present my part of my PhD work on my progressive colloidal clogging mechanism by dendritic buildup in porous media. Slide, it's not moving, sorry. Yeah, so the principle of geothermal energy is the production of hot water, and after heat extraction, the water is re-injected again into the reservoir. And due to changes in thermo and hydrodynamic conditions between the injected water and the water found in the subsurface, fine particles can emerge and they can seal the pores near the well, and that will decrease the injectivity. So as you can see on the right, the particles can lie in the suspension, or they can deposit on solid walls, and that will create clogging of some pores, redirection of local streamlines, and that will decrease the permeability. So understanding particle migration and the clogging is significant to prevent undesired formation damage, leading to injectivity issues in geothermal systems. So particle clogging in porous media, they can happen through different mechanisms. Sieving, when a particle is larger than a pore throat. Bridging, where multiple particles arrive simultaneously at the pore throat, forming arc-like structures. And by progressive clogging, where particles start to deposit, forming multi-layer accumulations of particles at two deposition sites at the entrance of the pore. And this is highly dependent on electrochemical interactions, and eventually it will clog the pore. So dendritic structures, they are a form of multi-layer accumulations of particles, and they are characterized by having a finger-like structures. So multiple colloidal studies, they have investigated different deposition patterns, and dendritic structures were one of them. As you can see here in these two figures, so they investigated that on an isolated grain collector and as well at the entrance of a 2D microfluidic filter. So they found that these structures, they can form under high salt concentrations where particle surface charges are screened, relatively high Pictet number, but not very high, because that will change the growth of the dendritic structures. And it's also dependent on the flow direction. As you can see in the second figure, when we will have a cross flow filtration, the dendrites are a bit oriented facing the flow. So the knowledge gap here is that researchers have seen these emergence of dendritic structures in simple like isolated collector and entrance of microfluidic filter. However, our question here is that what is the impact of the growth of these dendritic structures on the flow dynamics, however, within in tortuous porous domains? So we did a microfluidic experiment inside our lab, and we found that we inject particle suspensions at a relatively high salt concentration. And we found that there is emergence of dendrites forming upstream the grains facing the flow almost everywhere inside our porous domain. So that has led us to have the threefold research objectives. First, we need to evaluate the potential for these dendritic structures to clog a pore in this heterogeneous porous domain. Second, we need to identify the conditions that are responsible for forming these dendritic structures. And third, which is to analyze the impact of these structures on the overall system performance. And to do that, we have designed a heterogeneous tortuous porous domain, which mimic the complexity of subsurface formation, as you can see here in the figure. And we use PDMS. We form it in PDMS using soft lithography techniques. And what you see on the right, these are our geometric and hydraulic characteristics of our heterogeneous porous domain. So our flow experiments, they involve the injection of polystyrene particles coated with carboxylate group of a diameter of 4.5 micrometers. We dilute this stock suspension with the density matched fluid in order to avoid sedimentation inside our microfluidic device, and that until we reach to 0.12% volume fraction in 100 millimolar salt concentration. We inject our particle suspension inside our microfluidic device, and we take image sequences at specific pore volumes injected using a fast-take camera. Then these image sequences are imported into ImageJ and house built-in MATLAB codes in order to extract quantitative data and porosities. And then the images as well are imported into OpenFOAM to perform fluid flow simulations. As you see here as well, like we mounted two pressure sensors upstream and downstream the microfluidic device, which will allow us to measure the increase in pressure drop due to particle depositions and declogging throughout our experiments. So we inject our particle suspension at a specific flow rate, as you can see here at 8 microliter per minute, and we tend to track the particle deposition, the evolution of particle deposition and declogging with respect to pore volumes injected. So the flow is from bottom to top, and we tend to concentrate on a specific region of interest, which is in the yellow box here. So after the injection of 400 pore volumes under this specific hydrodynamic condition, we observe the emergence of dendritic structures forming upstream the grain. And then with time, with more pore volumes injected, we see that this dendritic structures is extending upstream the pore space until it will reach to an extent where it will be very close to the adjacent grain, as you can see here in the video. And however, no clogging happens yet because we can still see some particles passing between the dendrite tip and between the adjacent grain. However, after sufficient time and after sufficient pore volumes injected, we observe that we have achieved a full pore clogging of this pore, and we have a complete redirection of local streamlines. So what is interesting here is that this is a progressive clogging mechanism. However, it is emerging from a single deposition site until complete clogging takes place. We did another experiment at a higher flow rate at 20 microliter per minute, as you can see here. At the same region of interest, we observed that there is absence of dendrites and absence of multi-layer buildup. So our findings, they suggest that, okay, so the progressive buildup of dendrites from a single deposition site, they can eventually clog some pores, however, under specific flow conditions. So now the question is that how can we isolate and quantify the key factors driving dendrite formation in porous media? So we did experiments, flow experiments with the same particle suspension that we used before, however, here on a single grain collector. And we tend to investigate the particle depositions after the injection of around 2,400 pore volumes, which is the same pore volumes that we injected for the heterogeneous pores domain. We investigated that at 3 different flow rates. And we observed that at 1 microliter per minute, there is the emergence of dendrites upstream the grain facing the flow. And when we increase the flow to 5 microliter per minute, we observe that there is only a monolayer of particles that they are forming with no particle-particle attachment. And at 10 microliter per minute, we observe particles they are depositing at the rear part of the collectors. So in order to establish a quantitative basis from our experimental observations, we tend to combine the drag torque, which is responsible for mobilizing a particle from a surface, with the adhesive one, which is responsible for binding a particle to a surface or to another deposited particle. And from that, we achieve a critical detachment velocity, which can be between a particle and the surface, and the particle and another deposited particle. So what does it mean is that if the velocity of the particle is lower than this critical velocity, it will attach, and if it's higher, it will detach. So in order to identify stagnation regions that they are responsible for particle-particle attachments, we tend to perform fluid flow simulation by solving Stokes' equation, and we normalize the velocity fields achieved with the critical velocity for particle-particle attachment. A prerequisite for this, for identifying these stagnation regions, is to have a monolayer of particles surrounding the collector in order to promote particle-particle attachment. So what we see here is that at 1 microliter per minute, which is the flow rate which is conductive to dendrite formation, we observe a stagnation region which is cone-shaped. And this stagnation region, it is large enough that it can accommodate at least 1 particle diameter. However, as we increase the flow rate, we observe that this stagnation region, it is suppressed and it cannot even accommodate a single particle diameter. So the criterion here, the hydrodynamic criterion, is that in order for a dendrite formation to form, it needs to have a stagnation region which is coned, as well as it should accommodate at least 1 particle diameter. So the question is that, is this criterion applicable in heterogeneous porous domains? So for that, at the flow rate of 8, we did the same analysis, basically with the single, like the one that we did in the single grain collector. We normalized the velocity fields with respect to the critical velocity for particle-particle detachment. And we observed that at flow rate of 8 microliter per minute, where we had dendrites almost everywhere in the porous domain, in this specific region, we found that the stagnation region, they have this cone shape and they can accommodate around 1.5 particle diameter. And that had led to the formation of dendritic structures and dendrite clogging in this particular pore. And as you can see below in the small portion, small area of the heterogeneous porous domain, we observe that we have dendritic structures in black almost everywhere inside our porous domain. However, at 20 microliter per minute, we observe that this stagnation region is suppressed, leading to the suppression of multilayer buildup and the formation of dendrites, where there is absence of dendrite formations here. So we can say that dendrite formation to form, they require a cone stagnation region, which is large enough that can accommodate at least 1 particle diameter in order to promote particle-particle attachment. So to assess permeability damage at different flow rates, we applied the Verma-Priest model, which is a permeability porosity relationship, where phi here is the normalized porosity with respect to times on pore volumes injected. K0 is the initial permeability of our system of microfluidic device, and Kc is the residual permeability when we have a stabilized pressure after specific pore volumes injected. So the permeability here, it's inferred from the delta P measurements, pressure difference from our pressure sensors. and porosity, they are extracted from binary images. So we fitted our experimental data into this model, and we tend to achieve an exponent decay of around 3.75, as you can see here in blue, where we have where there is presence of dendrites and multilayer buildup. It means like we have a faster permeability decay at this flow rate at 8 microliter per minute. However, in red, at higher flow rates, we observe a slower permeability decay with an exponent of 1.32. So we can say that more permeability damage is observed for flow rates that they can promote the formation of dendrites and multilayer buildups. So as a conclusion, we have provided an experimental evidence of a new version of progressive clogging mechanism by dendritic buildup in tortuous porous domain, however, from a single deposition site. We established a flow-dependent criterion which promote the dendritic structures, and we showed how the presence of dendrites and multilayer buildups can accelerate permeability loss in the system. And for more information, you can check our published paper in Soft Matter, Journal of Soft Matter. And as a perspectives for this work, we would like to investigate the extent for which dendrite formation and dendrite clogging data can translate in three-dimensional environments, like in column experiments. We would like to investigate the impact of particle surface properties such as surface charge, shape, and roughness on the stability of these dendrites. And as we did our experiments at a controlled flow rate, what would be the effect on the dendrite formation if we did that in uncontrolled pressure? How the driving mode will affect the formation of these dendrites. And last but not least, I would like to take this opportunity to highlight as well my recent study on how oscillatory flows control clogging in porous media. So this work examines two key questions. The first one is that how frequency can govern clogging dynamics, changes in frequency. As you can see here, we first have continuous 0.1 hertz, 0.01 hertz. And the second one is that how the physicochemical regime modulates this response. So I will present this study at Interpor next month in Nantes. And I would be very happy to see some of you there and to discuss these results with you. Finally, I would like to acknowledge funding from the ERC on the Coconut project, which my PhD is part of it. And I would like to thank you for your attention, and I'm glad to answer any question. Thank you.
Thank you very much, Walid, for this wonderful talk. It was really, really interesting to see all these beautiful images and beautiful results. Thank you very much for that. So I'm encouraging anybody who is connected online to post their questions in the comments, and then I can read them out loud. Well, let's start with some acknowledgement of your work. Everybody is very happy about what you showed. We have a few comments saying that everything was super interesting and that the talk was extremely nice. I will just post them these randomly. And while we wait for some questions, I will start with a couple of questions of my own, maybe.
Yeah.
So I'm not an expert in colloidal filtration, but I'm wondering, I mean, have you tried also using different sort of geometries of the porous medium, and how is the heterogeneity in the geometry of the system somehow controlling the formation of these dendritic structures, if it does control it in any way?
Yeah, so for sure, yeah, the geometry, it will affect the formation of these dendritic structures. So especially because in our study, the mean pore diameter, it was around 100 micrometers. So for example, if we have smaller pore diameters, it means like at specific flow rate, if we use this specific flow rate in another heterogeneous porous domain, which is more confined or more have a more higher constriction ratio, I think that will increase the velocity, and by increasing the velocity, it will affect the growth of the dendrite formation. So I think, yeah, but we didn't do experiments on different type of geometries. We just stick to simple geometries in order to isolate conditions, which is the single grain collector, and one heterogeneous porous domain with specific pore diameter.
Yeah, yeah, yeah. Thank you very much for that.
Thanks for the question.
And there's a question from Marcel.
Okay, so very nice. So Walid, I was just wondering. So you've hinted there at the end that you intend to characterize how the surface properties of the particles affect, right, like the type of surface charge and so on. But just like from your experience, like from what you've seen so far, do you feel that did you have to fine tune the particles too much for the effects to be present, or is this something that's most likely if you get some random particles that just happen to be buoyant, they will end up clogging for some domain of particular numbers?
Yeah, so for example, the particles that I use, they are functionalized by carboxylated group. It means they have negative sign. When we increase the salt concentration, the zeta potential will decrease. It means they will attach more faster. So if we use different signs or different type of functionality, that will affect the particle-particle interactions, and that might affect the growth of dendritic structures.
Right, so it's the surface charge and the surface properties are definitely
so they will definitely affect the particle-particle interactions. So it's from the LVO theory.
I was just wondering, so you showed with the clogging that it blocks, right? So no particles go through once it completely blocks. But is it also clogging for the fluid entirely? Do you know if is the dendrite itself kind of like a porous medium that the fluid could go through just much harder, or is it really like a wall?
Yeah. So I can just show you the. So yeah, for example, if we concentrate here on this dendritic structure in the second video. So basically, because what we use here, it's in our microfluidic device, it's 2.5D. It means the depth, it's around 20 micrometers. So it's around 4 particle sizes, as I mentioned here in the slide. So the dendrite here, it is it's like a wall in the Z direction. For sure, the compaction of the particles, we can still have some fluids passing between the particles. But what we care here more about is that we manage to observe colloidal clogging by this structure, but for sure we will still have some fluids passing between the particles. Yeah. But imagine it it is in 2D. It will be like a wall. It's a dendrite, and it will be like a wall in between. For sure, we will still have some fluids leaking between the aggregates of particles.
Right.
But it will be much less
Yeah. Thanks a lot. Super beautiful experiment. I like it a lot.
Yeah. Thank you so much.
Really beautiful. Yeah, we have one question from Cyprian who is asking, what do you expect in 3D? Will we still observe the dendrites?
Yeah, so in 3D, I imagine we can still have we can still see the dendrites, I imagine, and I think this is the work that we are now in our lab. We work as well on filtration using column experiments, and it would be nice as well to be able to see if we can, at these specific conditions, to see dendrites in 3D, and to see if we can achieve as well dendrite clogging in 3D. So, but imagine in 3D we will not have a clogging of our pores. We will have it will be as a bridge between two grains, but that will affect the flow in the system, and it will increase the resistance and decrease the permeability. So that's, I think, it's ongoing work in our group, not the investigation of dendrites. We are doing colloidal filtration in column experiments, but it would be nice if we can manage to see that in 3D.
Yeah. I have one last question. Like you see mostly the dendrites forming upstream, right, of your grains. But do you see any forming downstream? Like I have in mind some experiments, not with colloidal particles, but with bacteria, for example, and they form mostly downstream the grains. I was wondering if you could maybe comment on that.
Yeah, so they are called streamers, I think. So in my experiments, I didn't see like these streamers, but yeah, I saw a couple of research paper. They got this like in bacterial growth at the rear of the collector. For me here in particle suspension, I didn't maybe at least at the hydrodynamic conditions that I'm using, I didn't experience to have the streamers. But yeah, it's possible. It's possible, I think. But what will be the hydrodynamic conditions? I have no idea, because for me, if we go back to my single grain collector experiments, you can see here some particles forming at the rear part of the collector, but we see them like just as a monolayer of particles forming at the back, and this was with high hydrodynamic forces. But we didn't experience like particle-particle interactions binding on the top of each other's, forming, for example, a dendrite or a multi-layer buildup on the back of the collector. Maybe in bacteria it might be a different mechanism.
Okay. Yeah. So thank you very much, Walid.
Yeah.
It was really impressive. Thank you so much.
Thank you.
So we can go ahead with the second speaker. So we thank Walid once again, and we move to our second speaker today, who is Moussa Hamieh. He's a second-year PhD student at the Laboratoire de Thermique Energie de Nantes, and his research focuses on thermal management and optimization of CO2 capture using MOF-based materials, and he will tell us all about those in a few minutes. And specifically, he combines experimental and modeling approaches to better understand multi-scale heat and mass transfer phenomena, aiming to develop efficient and scalable carbon capture systems. So today, his talk will be about the thermal optimization of CO2 capture using MOF materials, composites, and renewable energy sources for regeneration. So with this, Moussa, the floor is yours, and thank you so much for being here.
So, hello everyone. First, I would like to thank you for inviting me for this session. I'm Moussa Hamieh, second-year PhD student at LTeN Nantes University in France. And today I will present my work on thermal optimization of CO2 capture using MOF conductive material composites and renewable energy source for regeneration step. This is the outline of my presentation. First, I will introduce the context of CO2 capture, the material used, and the problematic in this process. Then I will discuss the thermal effects involved in the absorption process. After that, I will present my experimental work, including evaluating these thermal effects and also the electrothermal in-situ conversion for carbon materials and also for the MOF carbon material composites. And finally, I will conclude with the main results and perspectives. So first, let's start with the introduction. I started in this project as a PhD student in November 2024. It's funded by the French ANR and TEN-MOF project, and it's in collaboration with two other labs, the IMN at Nantes and the ICMN at Orléans. And it has objectives to enhance the thermal management in MOF-based materials, to optimize the energy-efficient regeneration techniques, to adopt a multi-scale experimental and modeling approach, and also to conduct at the end a life cycle assessment LCA. So to achieve these objectives, it's important to first understand the main limitation of the MOFs and how this limitation is related to the thermal effects occurring during the absorption and desorption process. So first, let's see the problematic. What is the absorption? Absorption, it's a process when we have adsorbates that are fixed at the outer surface of another material called the adsorbent, without chemical reaction, but by van der Waals forces. There is in the literature many physical absorbents that are very well known, like the zeolites, the activated carbon, and the metal organic frameworks. Here we will focus in this presentation on the metal organic framework, the MOF. So first, let's define what is the MOF. The MOF is they are solid microporous solid materials. They consist of metal ions and connected with each other with organic ligands. They are known by the high specific surface area, also by their tunable porosity. So with changing only the composition of the MOF, the metal or the organic ligand, we change the porosity to adapt it to the suitable application that we want. It's also known by its high selectivity for the CO2 among the other gases, but also it have higher heat absorption comparing to the other traditional physical absorbents. And this will cause a problem here because we have the absorption is exothermic process, it releases heat, and the desorption is the inverse, it's an endothermic process. Here it will lead to reduction in the absorption capacity. We will see it here how we have this reduction. Here we see two isotherm lines, one at 25 degrees and the other at 80 degrees, with something called temperature swing. This is temperature swing absorption. Is the process to absorb and desorb in our case. What does that mean? TSA or temperature swing absorption means that we absorb at low temperature, for example at 25, and we desorb at high temperature, for example at 80 degrees. And to desorb, we need the heat, so we heat our sample to reach the temperature suitable for the desorption, and then we desorb the CO2 already absorbed during the absorption phase. Here we should note that the TSA, temperature swing absorption, is known as a process that it's more effective than the pressure swing and the vacuum swing absorption, but also it requires too much energy, and this is a limitation in this process. So let's go back to our isotherm, and here we have a low temperature, and at low temperature we have higher amount of CO2 of gas absorbed comparing to the isotherm with higher temperature. What's happening here during absorption, the heat is released because it's exothermic, and since MOF it's not a thermal conductor material, then the temperature of the MOF increase and we risk have hot spots. And then if since it's increasing, so it passed from one isotherm to another with higher temperature, and this isotherm have a lower a lower capacity absorption for the gas, so the MOF is more likely to desorb instead of absorbing. It will be the inverse during the desorption. We want to heat, so during the desorption, the MOF will be cooled down, so it will move from one isotherm to another with lower temperature, and it will the MOF will be likely to absorb instead of desorb the CO2. So these thermal effects are not at all negligible, because as we see here in this reference, here we have the isotherm lines absorption of CO2 uptake. For the MOF 5, we have from 25 degrees to 100 degrees. These are the isotherm. We see, for example, at 20 degrees, for example, we have absorption capacity of 17 millimole per gram. And with heating the sample or increasing the temperature, for example, at 80 or at 100, we have at the end about from 7 to 9. So here we are losing about 50% of the absorption capacity of the MOF. And this is not at all negligible. So the question here becomes how we address to the heat management during absorption and desorption, and how can we reduce also the energy cost of the TSA process. To answer this question, this is where carbon materials can play an important role. So carbon here is multifunctional. First, it improves the thermal conductivity, which enhances heat transfer during absorption and help also distribute and diffuse the heat generated because of the absorption. Second, we also electrical conductivity will be enhanced. This allows electrothermal conversion in situ through Joule effect heating, so bypassing only current at low voltage and current. So it's the type of photovoltaic PV, so it's a renewable energy source. It also enhances the absorbance of our material, the MOF. So it can absorb also direct solar energy, which will help us in the thermal regeneration. And finally, it provides a support for the MOF, since the MOF initially they are in powder form, So with the carbon, they will be shaped in pellets or plates or whatever you want. So it will provide the mechanical support for the MOF. So as we see here, combining MOF with carbon material allow us to first manage the thermal effects during the absorption and open the way to renewable energy sources for regeneration with low energy cost for the step of this option. So after understanding the impact of thermal effects and how we aim to address them, we first need to quantify these effects experimentally. Because of that, we developed the following experimental setup. This is a double envelope stainless steel cylinder, which allows circulating cooling water from a thermostat bath to control the temperature of the cylinder. Here at the top, we have an infrared camera to monitor the surface temperature of the sample. And we have the material is placed on aluminum support, which includes under this support a heating resistance for controlled heating, as well as cooling tubes also. So here, to measure the temperature inside the sample, we placed 4 micro thermocouples of 80 micrometer diameter at 1 millimeter each. And we can inject in this cylinder both pure CO2 or mixture of CO2 and nitrogen mixture gas. So with this setup, we will measure temperature difference for different first MOF and MOF carbon compositions with varying the percentage of the carbon inside the composite. We will test this in different operating conditions, insulated or cooled. So in the case of insulated, we will add like a Teflon support on the aluminum to work on insulating conditions, or cooled by letting only the support of aluminum with passing water in the cooling tubes here, this to maintain at maximum possible the temperature during the absorption. So we'll compare everything here. Also, with this setup, we will add later in 1 month the CO2 analyzer. So with the CO2 analyzer, we will be able to correlate the results of temperature changes during absorption and also the amount absorbed for different sample studies when we add the CO2 analyzer at the outlet of the cylinder. So here, as first experiment, we have the Teflon. We put the Teflon, as I said before, to be able to reach the maximum temperature possible in absorption, since aluminum will try to absorb the heat generated during the absorption because of its high thermal properties. So first, we need to heat the MOF for 6 hours under nitrogen. Why we need to do this? Because MOF initially is saturated with water molecules at ambient conditions. So the pores are blocked by the water molecules, and the CO2 cannot be absorbed by the MOF. So we should activate the MOF by heating and removing these water molecules. Because of that, we heat under nitrogen for 6 hours. And then after this activation, we will wait until the MOF is cooled down till ambient or 30 degrees, and then we will inject the CO2 at 1 bar. Here, as first experiments, what I did is I injected directly from the bottle of the gas. So here, no mass flow controller. And also, then I used a mass flow controller at 133 milliliter per minute. So for the case of direct from the bottle, we see there is a huge increase from 30 to about 85 to 87 degrees. So we are talking about more than 55 degrees of delta temperature, which is not negligible at all. And when we add the mass flow controller, we see that the increase was lower, so about 40 to 42 degrees. And also it's slower. It's not the same slope of increase in temperature. So here we cannot compare the real behavior of absorption because we don't have the data of the quantity absorbed. So the CO2 analyzer here is needed to see the difference of behavior between the two cases. But this also gives us an idea that the mass flow rate is also a parameter involved in the behavior of the materials, since it depends if the CO2 fill the entire volume of the cylinder before the required time to the MOF be heated, and so the temperature is increased in the MOF. So here to do is we will compare at different mass flow rates, for example, from 100 to 500. We will compare the results, and also not only CO2, but mixture of CO2 and nitrogen. Later I just wanted to visualize with camera the increase in temperature So this is we are here talking only about the first experiments. So here it was the support of aluminium. I put half MOF and the half with the carbon material. And for sure, after activation, I injected the CO2. And as expected, for sure, we see that only the part of the MOF is heated and not the part of the carbon. So as a plan for this experimental setup, we will compare the pure MOF and different composition of the carbon in the composites. We will compare between the Teflon and the aluminum, as I said, insulation and without insulation. We will compare the behavior when adding the cooling water under the support of aluminum also, and we will check for different mass flow rates. At the end, everything, we will repeat all the experiments when we will receive the gas analyzer to correlate the results to understand better what happens in each case. So far, we focused on the absorption and associated thermal effects. Now we will move to the desorption step and where the heat is required, and we investigate the electrothermal in-situ conversion as a regeneration method. So here we have a carbon matrix. So we have the carbon matrix. We have two copper wires connected to a DC power supply. We tested here three densities of matrix of carbon matrix from 52 to 184 kilogram per meter cube under two different current, 5 and 12.5 ampere. We see that lower density leads to the higher temperature because we know lower density leads to lower electrical conductivity and so high electrical resistance, and therefore with high electrical resistance we have more heat generated through the Joule effect. And also, as expecting for sure, when increasing the current, we increase the energy from Joule effect, so we reach higher temperature. So overall, both densities and current strongly influence the heating behavior of the carbon matrix material. To understand better this behavior, we look also at the electrical resistance of the material in the circuit as function of temperature and for the different densities. And we see clearly that lower densities correspond to the higher electrical resistance, and when increasing the density, we have lower electrical resistance because it's high anisotropic, so high electrical conductivity, and this explained the previous results. So the next step was to integrate the carbon after we understand the carbon and the behavior. Next step is to integrate the carbon with the MOF and evaluate the behavior of these composites, MOF and carbon. So we first compare the behavior of the MOF alone. So here it's the temperature of the MOF in function of time. And the current, no current was flowing in the MOF alone. So we have no increase in temperature. This is because the MOF is electrically insulated. However, when we added the carbon, we can see here clearly that the current flow inside the material of MOF carbon matrix. And we see that the temperature is significantly increasing to the desired temperature for the desorption step. So this confirms that the carbon enables the electrothermal in-situ heating for the composite. And to understand better, we analyze also the electrical resistance of the different composites for 10, 12, and 15% of the carbon inside the matrix, inside the composite. And we see with higher carbon amount, we have it's more electrical conductive, and we have lower electrical resistance. And at the end, it will depend from the voltage and the current applied to reach the temperature desired. Finally, we verified, after we saw that it was working by thermal conversion, we verified whether this heating it affects the material structure or not. So we test XRD, and the XRD shows that the crystal structure remains unchanged after more than 10 cycles, and also one long constant cycle at 100 degrees for 6 hours, because this is like the simulation for the desorption step, because we will heat for many hours to dissolve the CO2 already absorbed. So this was a simulation. And then the XRD shows that the crystal structure remains unchanged. So overall, MOF carbon composite enabled efficient electrothermal conversion in situ, and the performance can be tuned by composition, and the materials also remains stable under the operating conditions. So after confirming talking about the thermal effects and also the electrothermal conversion, and the material remains stable after these cycles. Now I will summarize the main results and perspectives. First, we confirmed that the thermal effects occur during CO2 absorption, leading to a temperature increase. However, the CO2 uptake is still unknown, so gas analyzer will be needed to correlate the results between temperature change and the CO2 uptake. Second, we have demonstrated that electrothermal conversion is applicable to the MOF carbon composites, enabling efficient heating for the desorption. Third, we showed that the material structure remains intact after multiple Joule heating cycles, confirming its stability by the X-ray diffraction. And as perspectives, future work will focus on optimizing the system design, particularly the geometry and the electrode configuration, to enhance the current distribution and the heating efficiency during the desorption step. And at the end, we will also explore coupling with direct solar energy for the thermal regeneration. Thanks for your attention.
Super, thank you very much, Moussa. And I welcome the audience to type in the questions in the comments field on the right-hand side of the screen. I have a quick question myself before. So you mentioned, you showed like this, the cell, right, with the closed cell in a diagram. And you mentioned at some point that you had like an infrared imaging.
Yeah.
Where does the infrared, like the cell is not infrared transparent, right? How can you get the infrared image? Right.
In this slide, you mean? Yeah.
Yes.
Yeah,
So
sorry, what was the question?
Is this like the top of the cell or the inside of the cell that we are seeing?
This is the top surface of the material that we have.
Right, but if you get back like to the slide with the cell and like this diagram of the
this one.
Yeah, there. I didn't understand, like, because the cell itself is metallic, I suppose, right? So it's not infrared transparent. So how can you see?
Okay, here first this double envelope stainless steel material, we put a black color to avoid the reflection to the camera infrared, and the support is filled with our material that are in powder. So here we have a powder material here, and the camera is only facing this powder material with with the distance of the working distance, and with entering the right values of emissivity of our material, we will see the temperature increase. And here we are working now on measuring the emissivity in function of temperature, because we know that it will change a little bit. I have some problems with the camera, so now I am yes, we are checking this problem. We will measure the emissivity in function of temperature.
So the camera is inside the cell. The camera sees
inside. Yes, here we put we drill the camera inside the cell.
Right.
It's like that. No.
Okay.
We kept like a small like about 5 centimeter because we know the dimension of the camera, and we drill the camera inside the system.
Nice. Yeah, very cool. Super. Thanks a lot.
Do
we have any other questions? I don't see any questions. Chat.
Yeah, I have a curiosity. So, Moussa, you were mentioning at a certain point that you tested, if I got it right, different composite materials, carbon composite with different densities of carbon, right? Exactly. And that you had like some anisotropic response. And I was wondering, I mean, is this anisotropy that you see related, because you relate that to the density of the carbon somehow, but is this related like to the anisotropy also in the structure, in the crystal structure of these composites, or?
Okay. I mean, first, the carbon material is in powder form, the carbon, and when we compress it mechanically, the flakes they will be oriented. So if we compress more, we will have more dense material, and they will be oriented, and the planes will be like more established or parallel. So we'll have two properties. This one, it's through in plane, it's radial, it will have better properties. And in the perpendicular one, axial one, it will have like low thermal conductivity, low electrical conductivity. So it depends on the density, on the compacting force of contact.
Okay, right. I see. Okay, I got it now. Thanks.
Yeah, right.
Okay, so if there are no other questions, let's thank Moussa again, and also Walid, speakers of today's session. It was very nice. Thank you. So before we finish, to remind everyone about the coming webinar at 4, so in just 1 hour and 10 minutes. And you can get the link to attend if you go on the Winterpore website and then click on Academy Webinar, and you have a Zoom link there. So yes, 4 o'clock today. And with that, I want to once again thank the whole team of the Tea Time Talks for organizing. And if you want to be a speaker or if you'd like to recommend a speaker, please get in contact with us. We are constantly updating the list of future speakers. Our email is porousmediattt@gmail.com. And the next session, I think it's in May, right? So mid-May probably. And
May 5th should be something like that.
May 5th. Okay, yeah. So that's in too long, 2 weeks maybe. And you're going to hear about it through our social media channels. So thank you very much, and I'll see you in Interpore in 1 month, right? 1 month from now. Okay. Bye.